Okay, and so we're going to start looking at how when two things collide, do you know what collide means? Two things hit each other, right? That's a collision. When two things hit each other, the momentum in the total system is conserved. So it doesn't mean that one object is still going to have the same momentum it had before the collision, but it does mean that in the total system, between the two objects and between the environment, we have a conservation of momentum, okay? It does not matter what something weighs or how fast it's going, the mass or the velocity. It doesn't really make a difference in that. It's always going to be that the total momentum before is going to equal the total momentum after some collision. Okay? So here's our main equation for momentum. M1v1 plus M2v2 equals M1v1 prime plus M2v2 prime. That's what that little apostrophe right here. This is called a prime. And take a guess on what do you think that means? Any idea on what the prime symbol means? Just based on context here, before and after, right? The prime means that this is our final velocity. Okay? Sorry. The 1 just means of object number 1, and the 2 means object number 2. It doesn't mean before and after, right? 1 means of object number 1, 2 means object number 2, prime means final, right? So you could have put an F there for final, but the way that most, where you'll see this equation written with most textbooks and everything like that is with this prime symbol, okay? So we could use this with however many objects were colliding, right? If there were 3 objects colliding, we would say M1v1 plus M2v2 plus M3v3, right? We could do as many terms on either side as we need. Most of the time, our collisions right now are just going to be between 2 objects. It's going to be pretty simple, but you could add more if you absolutely needed to, okay? If there's 3 things that are moving and we see a collision, we could add a term to that. Second thing we need to think about is that for most of the time, we're going to see like a true collision, right? Things are actually hitting and moving apart or sticking together, whatever. But some things that could be considered a collision would be like an explosion, right? If an object is sitting at rest and then it explodes, what happens to all those pieces? Do they usually go in the same direction? No, right? They're going a lot of different directions. So the combination of those momentums of those objects would equal 0 because at the beginning, before that collision, before that explosion, it had 0 momentum. And so we're going to kind of look at what that looks like. So we use the word collision to describe, yes, 2 things colliding, but we also use it to describe any sort of like quick change in momentum. Does that kind of make sense? All right, let's start with the 2 types of collisions. The first of which is called an elastic collision. Okay, I didn't put a definition in there for elastic collisions. But elastic collisions is when 2 things end up apart. Okay, maybe write this in to the side here. Elastic collisions is the things or whatever they are, the objects, end up apart. Okay, they end up separated. Sometimes when things collide, they collide and stick together and move in a certain direction. An elastic collision means they collide and then they end up apart, right? They could end up moving in the same direction, but they're still separate objects, okay? So let's try this one. Find the recoil velocity of a 5-kilogram rifle that shoots a 0.05 kilogram bullet at a speed of 120 meters per second. So in this case, what do you think the collision is? When does the collision happen? Or what we call the collision?
When the bullet's shot.
Right, exactly. When the trigger is pulled, right? Trigger is pulled, boom. That's the collision. So both of our objects here really start at rest because nothing is happening before that trigger is pulled, right? And then I want you to visualize what happens. Do you know what a recoil velocity is? What a recoil is? So I shoot the gun, and then what happens to the gun? It's called a kickback, right? It kicks back at you. So you fire the gun. All of the force that's used to push the bullet out has to come back somewhere, right? This is Newton's third law. For every action, there's an equal and opposite reaction. So when I fire the bullet goes out with a lot of speed, little mass, right? But now this big, heavy object's got to move somewhere, so it kicks back. And so that's the speed that we're trying to aim for here, okay? So as we go through these problems, I like to kind of make myself, I like to make a list of what I'm doing here. So let's call, which one do you want to call the first object, the gun? Okay, so M1 has a mass of 5 kilograms. M2 has a mass of 0.05 kilograms. I will say that we want to make sure that our masses have consistent units. Usually we're aiming for kilograms. If we go with grams, not the end of the world, but they at least have to be consistent. Okay, if we would go grams, that means that our momentum unit would be grams times meters per second. So it's a little bit different there, but we want to aim for consistent mass units. So most of the time, just go ahead and make sure everything is in kilograms. Okay, initial velocity of the first object or of the gun is 0. Initial velocity of the bullet is 0. We don't need to write the mass again, right? Because the mass is not changing. But V1 prime, right? That's the mass of the gun after the collision. What's that going to be? Yeah, that's right. We don't know. That's what we're solving for, right? That's my question mark. And then V2 prime is 120 meters per second. We're going to assume that the bullet's direction is the positive direction, right? We'll just make that the positive direction and we'll find the gun's velocity. So can we anticipate anything about the gun's velocity? What direction do we anticipate it being? It's going to be negative, right? The bullet's going forward, the gun's going backwards, right? So at least we can anticipate that much of it. So let's go ahead and set up our equation here. We know that M1 times V1 plus M2 times V2, right? We know that whole side's going to be 0. So if you don't want to write out that whole part of the equation, that's no problem. But you can, so you thought about it. M1 times V1 prime plus M2 times V2 prime. And so I'm going to have an equation that says 0 equals 5V1 prime plus 0.05 times 12 is probably, times 120, 6 something. Oh, exactly 6. Okay, so now how can I rearrange to solve for V1 prime? I'm going to subtract 6 to the other side. So now I'm going to, let me move up here. Now my equation is going to read negative 6 equals 5V1 prime. And so I'll divide by 5. And my final velocity of my gun then is negative 1.2 meters per second. So if you would take the velocity, if you would take the momentum of my gun, negative 1.2 times 5, that gives me negative 6. We already said that my momentum of my bullet, 0.05 times 120, is positive 6. So add those together, and that gives me the initial momentum of my system, which was 0. Right? So that's what we talk about when we say the momentum was conserved, right? We see 0 momentum to begin with, and then these two objects after the collision or the firing of the gun have 2 momentums in opposite directions, which add up to 0. Okay, so that's what we talk about when we say conservation of momentum, is that both before and after, the total momentum in our system is the same. Okay? The thing you have to know about elastic collisions is that these two objects are going to end up apart. Okay, we're going to look at another type of collision in which they end up together. Okay, but these are collisions in which they end up apart. Okay. 2 pool balls of equal mass collide. The first is moving at a speed of 3.1 meters per second, and the second was at rest. If the collision was perfectly elastic and the first ball came to rest, what is the velocity of the second ball? Okay, so I want you to just visualize what's happening here. Pool ball is moving in this direction. This one's at rest, right? First one's in motion. This one's at rest. First one comes to a stop. The second one starts moving. Okay, so It's going to be a perfectly elastic collision. The first one comes all to rest. And so when we see a perfectly elastic collision, that also means that we had a perfect transfer of kinetic energy, right? Kinetic energy of one perfectly transferred to the kinetic energy of the other, right? That's what we're looking for in a perfectly elastic collision. Not all collisions are like that in real life, but in high school physics, we live perfect physics world, so most of our collisions are going to be perfectly elastic. Okay?
So do we even need to do the equation for that one?
Great question. No.
Okay.
Okay. Here's why. So she asked, do you have to do the equation at all? The answer is no, but the only reason the answer is no is because they are of equal mass. Right? That's really, really the part of it that makes the biggest difference, is that they're equal mass. So let me just run the math so that you can confirm that, right? You guys are right, but I want to show you with the mass. So let's just say they have a mass of 1 kilogram to make it easy, right? The first object is moving at 3.1. The second one is at rest. It says the first ball comes to rest, so 1 times 0 plus 1 times 3.1. Okay? The second was at rest. The first one, we're trying to solve for this guy, sorry. V2 prime, right? We're going to solve for that. So we're going to say, we know they have equal mass, so we just picked a mass. That gives me 3.1 equals 1 times V2 prime. Okay, so I divide that by 1. That means V2 prime is equal to 3.1. So my collision being perfectly elastic, this little trick works when they have equal mass. Okay, good question. You need to look for the term perfectly elastic, and you need to look for the term equal mass in order for that to be true. Okay. A 22 kilogram bat is swung with a velocity of 16.2 meters per second at a 9.4 kilogram ball, moving in the opposite direction of the bat. If the ball leaves the bat with a speed of 42 meters per second, what is the final speed of the bat? Okay, so there's a lot happening here. The bat is moving in one direction. The ball's coming the other direction. Ball hits the bat. Ball flies opposite direction. What do you think is going to happen to the bat? Is it going to come backward or is it going to continue forward? Right? It's probably going to continue forward, but let's see. Right? Okay, so do you want to call the bat object 1? All right, so let's say that M1 is 22. Initial velocity of that bat is 16.2. So we have to identify here, what's the positive direction? Is the positive direction toward the outfield, or is the positive direction toward like home plate? You know what I'm saying? Is the bat moving in the positive direction to begin with, or is it moving in the negative direction? Okay, so let's pick that direction. Can you guys visualize the baseball field that I'm talking about? Right? Visualize the bat moving in that direction as positive. So that means this is going to be a positive 16.2 meters per second. And then what happens to the bat after the collision? Right? That's what we're trying to solve for. Okay, let's look now at the ball. M2 equals 0.94. My initial velocity of my ball was moving opposite of my bat at 34. So that means I need to plug in negative 34 meters per second there, right? Directions make a huge difference with momentum problems, right? We've got to make sure we're doing our directions correctly. Any questions about why those two need to be opposite directions? Right? Bats swinging this way, balls coming this way, they have to be opposite. The ball leaves the bat at a speed of 42 meters per second. It doesn't give us a clear direction here, but what can we assume? That the ball is moving in the positive direction. So we're going to call V2 prime positive 42, and that means I'm going to go ahead and solve. So 22 times 16.2 plus 0.94 times negative 34 equals 22 times V1 prime plus 0.94 times 42. All right, so let's run the math on the left side here. So I got V1 prime to come out at about 12.95 or roughly 13 meters per second. Is that what you guys had? Okay, I'll combine my like terms, which are 1, 2, 3, and then I'm going to divide by 22. And we were right? We said that the bat's going to continue to move in the positive direction. The reason that is because look at before the collision. Look how much more momentum the bat had than the ball. Right? Can you see what's happening there? Number one, the bat is much, much heavier, significantly heavier, and moving just a little bit slower than the ball, right? So look how much more momentum my bat has beforehand. So when the ball comes, the bat not only has enough momentum to change the direction of the ball, but it also has enough momentum to keep its original motion, right? To keep its original direction. So it slowed down some after it hit the bat, but it still was able to move forward. Okay, we're going to see that happen when we have, two balls collide and one is much heavier and it's going to be able to change the motion of the smaller ball and it's going to get to continue on its path and things like that. So hopefully this one kind of makes sense to you in terms of the directions with that. Okay, inelastic collisions are things, I took this PowerPoint from somebody and they were really extra about their, look. Ooh, okay, yeah, it's not that cool. Okay. So they have objects, inelastic collisions are objects that collide and then stick together. Whether it's magnetic, whether it's wreckage and it sticks together, whether it's you tackle somebody and then you fall together or whatever it is, right? They stick together. So in this scenario, the red train is moving 24 meters per second, and it's going to collide with the blue train that is at rest. And then that's before, okay. I told you this person was been real extra. Ooh, okay. After the collision, the masses are connected. Yeah. Okay. Oh. Wow, I forgot about that. Every year that surprises me. Okay, I don't know why they did that, but okay. So this is our new equation for inelastic collisions. And I would go ahead and put this one on your equation sheet if you don't already have it. But we see one main difference here between our elastic collision and our inelastic collisions. What is it? Right, you see how here we've only got one final velocity, right? Why would we only have one final velocity for our system? Yeah, the masses are connected. So once they're connected, now we consider them as one object. So we take their masses, we add them together, and then we just have a single prime velocity, right? What's the velocity of the whatever, the one thing after the collision, okay? So this one, here's our red train, blue train. So if the red train has a mass of 30,000 kilograms, moving 24 meters per second east, and the blue train has a mass of 20,000 kilograms and it's at rest, what is the velocity of the cars after the collision? So let's try to think out loud with this before we even get to the math. Do we envision these cars continuing to move after the collision, or is it going to be just hit it and come to a stop? Continuing to move. I agree. Why do you think so? Look at the car that's in motion. The car that's in motion is moving pretty quickly and it's significantly heavier than the car that's at rest. Right? So let's think about this. I've got a lighter object at rest and I've got a heavier object that's going to hit it. So we're going to envision that our objects continue to move forward after that time. So let's go ahead and plug it in. M1, I don't think we need to make our list here because it's pretty cut and dry. M1 times V1 plus M2 times V2, which we know is 0 because our second car was at rest. Then after the collision, we're going to add those masses together. And we're going to solve for what's the velocity of my single object, right? Because they are stuck together, we've just got one single velocity there at the end. Okay, so it's just called V prime instead of V1 or V2. Okay, so this gives me about 72,000 over here on this side. Wait, that can't be right. 30,000 times 24, 720,000. Sorry, I missed a zero. Equals 50,000 times V prime. And so when I divide over that 50,000, I got V prime equal to about 14.4 meters per second. Agreed? And it comes out positive, so we assume it's continuing in the direction of the first train, which is east, right? Our velocity was smaller, right? This train systems was slowed down, but it still continues moving because that first one has so much more mass and it's moving with some more velocity than our second one. A 4 kilogram ball is moving at 5 meters per second north. It collides with a 6 kilogram ball moving 3.2 meters per second south. If the two balls stick together, what is the final velocity? So let's just start with our list here. M1, V1, M2 and V2, and then we're going to look for what's our prime velocity here. So M2 is 6, V2 is 3.2. I'll go ahead and just write these out. M1 is 4, V1 is 5. And then we're solving for what's V prime, right? We don't have a velocity final for each one. We just have a total final velocity. So we'll say 4 times 5. Oh, I missed something on my V2, didn't I? It's got to be negative because it's moving south. My bad. Okay. Plus 6 times 3 times negative 3.2. Equals 4 plus 6 times V prime. Okay, did I get those numbers plugged in the right spots? All right, what did we get for our V prime?
Wait a minute.
Yeah, I got 0.08.
Okay,
Yeah. We freaked out because it was too small.
Oh, Andy looked at me. She goes, "Wait, what'd you get?"
0.08 meters per second. And what direction are we thinking here? North, right? It came out positive, so we've got to include the cardinal direction. Since we were given a cardinal direction, we need to go ahead and put that in our answer, right? If we're not given a cardinal direction, then the positive negative is enough. It's sufficient. But if we are given a cardinal direction, we want to go ahead and put that in the answer as well, okay? So this one kind of makes sense. It's nearly coming to a stop, right? We've got two cars with similar initial momentums, right? This was 20, this was 19.2. So they've got similar momentums, just in opposite directions. So that one that was moving north just has a little bit more that it's able to kind of change that system. What if they would have had completely identical momentums in the opposite direction? What if it was positive 20, negative 20? What would have happened at the collision? If we have to say that momentum was conserved, what had to have happened after the collision? Right? If one has positive 20 momentum, what has negative 20 momentum? After the collision, what has to happen? They come to a stop, right? They have to come to a stop. Because if the sum of my initial momentum was 0, then that means the sum of my final momentum had to have been 0, right? So if that were the case, that would be an inelastic collision that brings it to a 0, but they've got to have identical initial momentums in opposite directions, right? That was not the case here, but I just wanted to explore that a little bit. All right, a 35-gram bullet. Make sure we see that to convert that to kilograms. Okay, can we envision what's happening here? A bullet gets fired into something, and then those things are going to stick together, and we're going to see, does the target move, right? Like this. Those things are going to stick.